Okay, in this video, I want to prove two more of the limit laws that are found in Theorem 3.3. In fact, you can find the statement of the theorem and the proof of all of the various parts here on handout number 13. So everything is actually proved already in handout number 13, and I proved in class part C that said that the limit of a product is equal to the product of the limits, provided that the two individual limits exist. And here I want to go through the details of part D and part E, though, as I said, the details are in fact already written down in handout 13. Okay, so to start, we'll prove part D, which says that if Sn is a sequence of complex numbers converging to S, then the absolute value of Sn converges to the absolute value of S. And note, as I said in class, that because the real numbers are contained in the complex numbers, all of these limit laws also hold for real numbers. Okay, so we're going to try and prove that this is true, assuming that this is true. All right, so proof. So we're supposed to suppose that the limit of S sub n is equal to S, and what we want to show is that the limit of the absolute value of S sub n is the absolute value of S. So how do we do this? Well, we let epsilon be bigger than 0, and then, because S sub n has limit S, we know that we can find a positive integer n such that whenever little n is greater than or equal to capital N, the distance from S sub n to S is less than epsilon. Remember that distance in the complex numbers is just given by this formula here. All right, so now we're going to claim that, in fact, this same capital N is going to work to give us this limit here. So suppose that little n is greater than or equal to capital N. Then what can we say? The distance from S sub n in absolute value to the absolute value of S is, well, in fact, we proved an inequality in handout number 9 that said that if you have any complex numbers, like these ones, then the absolute value that we see here of the difference of absolute values is always less than or equal to this. All right, so the distance between the absolute values of two numbers is always less than or equal to the distance between the two numbers. In fact, we prove this more generally in any normed vector space. So then, I'm just going to write up here, see proposition 12 in handout number 9. This is true. And because little n is greater than or equal to capital N, we know that the distance from Sn to S is less than epsilon. So on the right here we have something less than epsilon. So what have we shown? We've shown that given epsilon bigger than 0, we can find a positive integer capital N such that whenever little n is greater than or equal to capital N, the distance from the absolute value of S sub n to the absolute value of S is less than epsilon. Well, that's all we need to say that the absolute value of Sn the sequence of absolute values, S sub n, is equal to the absolute value of S. So that's all we need to prove I wrote part A. In fact, this was part D, wasn't it? So that proves part D. Okay, so we now want to prove part E of the theorem, the first part of which says that if S sub n is a sequence of complex numbers converging to S, with S not 0 and each S sub n not 0, then the limit of 1 over Sn is 1 over S. Alright, so what do we need to do? So we need to begin, as always, by taking epsilon to be an arbitrary number greater than 0. And what do we need? Well, we need, as always, to find a positive integer n such that whenever little n is greater than or equal to capital N, the distance from the nth term in our sequence, which is 1 over S sub n here, and 1 over S, is less than epsilon. Okay, so we therefore need to make this distance here epsilon small for large enough n. So let's start at first by taking a look at this term here. So observe that this distance that we're interested in, it's 1 over S sub n, the distance from 1 over S sub n to 1 over S, can be rewritten in the following way. We can find a common denominator, which would be the product S sub n times S, and in the numerator here we would then get S, and from the right we'd get S sub n. This we can rewrite as, remember, absolute values distribute nicely through products and quotients. So that's absolute value of S minus S sub n times the absolute value of S sub n times the absolute value of S. And I'll just rewrite that one more time as 1 over the absolute value of S sub n times 1 over the absolute value of S times, and this is the distance from S to S sub n, which is the same as the distance from S sub n to S, so I'm just going to write it like that. So the distance from S sub n to S. Alright, so what do we know? Well, we know that because S sub n is converging to S, we can make this small. So remember, what are we trying to do? We're trying to make this distance here small. In other words, we're trying to make this distance here small. And this is the same as what we have here. We know that we can make this part small because S sub n is converging to S. It's 1 over the absolute value of S shouldn't be a problem, given that S is not 0, and so the absolute value of S is not 0. Our only concern might be this part here, because we might worry that as this is getting small, this is getting big. So what we hope is that we can make this less than m for large enough n. If we can do that, then we should be able to make this entire product small. Well, notice that this would be, this entire quotient, 1 over S sub n, would be less than m if and only if when we take reciprocals, absolute value of S sub n is bigger than 1 over capital M. So in fact, if we can bound this absolute value of S sub n below by some number, doesn't have to look like 1 over capital M, of course. You can write it as maybe delta, for some delta bigger than 0. then if we can, so as I'm saying, if we can make the absolute value of S sub n always bigger than some delta, then 1 over S sub n should be less than, well, 1 over delta. Okay, so the question is, can we in fact bound this part by a number m? If we can, I think that we can probably make this entire quotient small. So what are we going to notice? Well, note that the absolute value of S sub n is converging to the absolute value of S by part D. Alright, so let's write that down. From D, because S sub n converges to S, the absolute value of S sub n is converging to the absolute value of S. Remember that absolute value of S is bigger than 0. So let's draw a little picture here. So say this is 0, and this is the absolute value of S over here, because the absolute value of S sub n is getting as close as we like to this absolute value of S, we should be able to make the absolute value of S sub n bigger than some delta for large enough n. In particular, if we were to say, take delta to be the absolute value of S over 2, it seems natural that we should be able to get our S sub n's larger than the absolute value of S over 2 for large enough n, given that our absolute value of S sub n's are converging to the absolute value of S. And in fact, if we want to be very careful about it, we notice that if we took delta to be this distance here between the absolute value of S and the absolute value of S over 2, travel in either direction in fact, then we know that we can make our absolute value of S sub n's within this distance delta of the absolute value of S by taking n large enough, just because of we have this limit here. Okay, so in fact, what would this delta be? Well, this delta, if it was the distance from the absolute value of S to the absolute value of S over 2, you calculate, you see that actually that delta is the absolute value of S over 2 itself. So let's write this down. Okay, so since the absolute value of S is bigger than 0, delta, taken to be the absolute value of S over 2, is also bigger than 0. Right? And we can take a positive integer, let's call it n sub 1, and n such that whenever little n is greater than or equal to n sub 1, the absolute value of S sub n is in the delta neighborhood about the absolute value of S. Why can we do that? Well, if the absolute value of S sub n is converging to the absolute value of S, given any delta neighborhood about the absolute value of S, we can find a capital N sub 1 such that whenever little n is greater than or equal to capital N sub 1, the distance from the absolute value of S sub n to the absolute value of S is less than delta, and therefore the absolute value of S sub n is in the delta neighborhood about the absolute value of S. Specifically, we've used theorem 3.2 part A prime, but really it's straight from the definition of convergence. Okay, well, what is this set? Well, this is the set absolute value of S minus delta, it's the left endpoint, absolute value of S plus delta as the right endpoint, which is equal because because delta is the absolute value of s over 2, this is equal to, well, absolute value of s minus the absolute value of s over 2 is the absolute value of s over 2. And the absolute value of s plus absolute value of s over 2 is 3 times the absolute value of s over 2. And therefore, absolute value of s sub n in particular is bigger than the absolute value of s over 2. Alright, so what do we have? We have that if little n is greater than or equal to capital N sub 1, absolute value of s sub n is bigger than absolute value of s over 2. And remember, we were looking for a bound 1 over the absolute value of s sub n. And this is going to tell us that 1 over the absolute value of s sub n is less than the reciprocal of this number, which is 2 over the absolute value of s. So let's write that down. So thus, if little n is greater than or equal to n sub 1, then 1 over the absolute value of s sub n is going to be less than 2 over the absolute value of s. And this is good because now, what do we know? We know that we now have a bound for 1 over the absolute value of s sub n for large enough n. And if we go up, well, if we go up, we see that, remember we're trying to make this distance here small, which looks like this, and now we have this bound for 1 over the absolute value of s sub n that we said we were looking for earlier. This m can be taken to be 2 over the absolute value of s. All right. So now we're going to use the fact that we can make this small here, and we should be able to finish up quite quickly. All right, so we have this statement right here. So now let's take n sub 2 to be a positive integer, such that whenever little n is greater than or equal to n sub 2, the distance from s sub n to s is less than, well, might not be quite epsilon, it might be some fraction like 1/2 epsilon. We'll figure out what that is later as we move forward. Okay, but we can do this, of course, because we're assuming that s sub n has limit s. All right, well, we're going to want both this condition here and this condition here for large enough n. So we'll do what we usually do, and we will take capital N to be the larger of n sub 1 and n sub 2. And let's suppose that little n is greater than or equal to capital N. Alright, so we're hoping that this capital N is going to work for us. Alright, so what do we need? Well, then what we're hoping is that the distance from 1 over s sub n to 1 over s is going to be less than epsilon. Well, from what we wrote above, we know that we can rewrite this as 1 over the absolute value of s sub n times 1 over the absolute value of s times the distance from s sub n to s. Right? Well, because little n is greater than or equal to capital N, and capital N was larger of n1 and n2, we know that little n is also going to be greater than or equal to capital N sub 1, so we know that 1 over s sub n, which is what we see here, is less than 2 over the absolute value of s. Alright, so this is less than 2 over the absolute value of s times 1 over the absolute value of s times, well, now what? Because little n is greater than or equal to capital N, we know that little n is also greater than or equal to n sub 2, so we know that this distance is less than whatever we decided to put here times epsilon. So we can write that this is less than something like this times epsilon, and what we hope is that this is equal to epsilon. So to make this equal to epsilon, it looks like I'd like to see absolute value of s all squared, that doesn't look too messy, over 2, because then these would cancel. Cancel, cancel, and cancel, cancel. So what are we going to write in here? We're going to write absolute value of s squared all over 2. Could we have chosen in this way here? Well, yes, because s sub n is converging to s, and the absolute value of s squared over 2 times epsilon is a positive number, we can definitely find a capital N sub 2 such that whenever little n is greater than or equal to capital N sub 2, the distance from s sub n to s is less than this positive number. So this is fine. We get this over here, and that's what we needed. All right. Just to recap very quickly, given an epsilon bigger than 0, we were able to find a positive integer capital N such that whenever little n was greater than or equal to capital N, the distance from 1 over Sn to 1 over s was less than epsilon, so hence the limit of 1 over s sub n is indeed 1 over s as needed. Now, very last thing that we need to show is this. We claim that if we also have that the limit of t sub n is equal to t, then the limit of the quotient t sub n over Sn is equal to t over s. So here as before, we're assuming that s sub n is converging to s with s not 0 and each s sub n not 0. Well, to see that, you don't have to work very hard now, because we can just use our earlier limit laws. So we have that the limit of t sub n over s sub n, well, we could write this limit of a quotient as limit of the product of these two sequences, 1 over s sub n and t sub n. And do we know? We know that t sub n is converging to t, and we also know that 1 over s sub n is converging to 1 over s from our last claim. And we also know from part C, which we already proved, said that the limit of a product is the product of the limits of sequences provided the two limits exist. We can write that this is equal to the limit of 1 over s sub n times the limit of the sequence t sub n, which, as we already said, is 1 over s times t, and that, as we said, is equal to t over s. And there you have it. The limit of the quotient is equal to the quotient of the limits. So that completes the proof.